In this video, we will learn how to write chemical equations for acids and bases, identify conjugate acids and bases, and then we will talk a little bit about acid and base strength. So in these reactions with our Bronsted-Lowry definition of acids and bases, we know that our base is a proton acceptor. And our acid is a H+ donor. And so when we write out the products, we know that this nitrogen is going to grab onto one of the hydrogens from water and become NH4+. And we know that water is going to be losing that H+ and becoming OH-. But if we look at this arrow between these two, this reaction can actually go both ways. And so that's represented by this double fishhook arrow. This chemical reaction can also go the other direction. So let's look at the backwards reaction and see what happens. As NH4+ turns back into NH3, it's going to be losing a proton. So for backwards reaction, so according to our backwards reaction, NH4+ turns into NH3, so it's losing a proton, and so it loses H+, which means it's a donor. So on the backwards reaction, it acts as an acid. And then our OH- gains a proton as it goes back to become water. And so our OH- acts as a base. And so then we look at this and we say, okay, my acid over here gets paired up with a base in the backwards reaction. We're going to actually call this the conjugate base. And we're going to call this the conjugate acid. So on the product side, you have conjugates. You're going to have conjugate acid, conjugate base. And so we find the acid on the reactant side gets paired up with the conjugate base. And the base gets paired up with the conjugate acid. So we call these conjugate acid-base pairs. Here's some practice problems for you. I want you to identify the Bronsted-Lowry acids and bases based on their reaction with water, and then label the conjugate acids and conjugate bases. Go ahead and pause the video and try to identify the acids and the bases, conjugate acids, conjugate bases in these problems. Okay, let's go over this. So let's look at how things change. So this compound has the sulfur, and so that's going to get paired up with this compound that has the sulfur. So what changed there? We went from having 2 hydrogens to having 1 hydrogen. And so it loses a proton. Since this one loses a proton, it is a proton donor, which means it's an acid. Water becomes H3O+. Water gains an H+, which means it's a H+ acceptor, which means it's a base. If we look at the reverse reaction, H3O plus, turning back into water, would have to lose a proton. So that's going to behave like an acid. And that means that we're going to have that we call the conjugate acid. Remember, on the product side, we label things with the word conjugate. And this, HSO4 with a minus charge, would be my conjugate base. Okay, let's go on to the next one. We have HCO3 with a minus charge. And so this one has a carbon, so that gets paired up with this one that has a carbon. There's a lot of hydrogens and oxygens, so sometimes you have to look for other elements to know how they pair up. And so the water is going to be paired with the OH minus. So this H2O loses an H plus. And so that means that water in this case is behaving like an acid. HCO3 minus, hydrogen carbonate, is gaining H plus. And so that's behaving as a base. As we come over to the other side, my acid gets paired with my conjugate base. And you can verify that by looking at the backwards reaction and seeing how OH minus has to get paired with H2O. And so normally we would write that as hydroxide. I wrote HO minus because I wanted you to see the same order of things. It might have been easier for you to tell that there's two hydrogens becoming one if I wrote it in that direction. I don't know. Anyway, and this would be our conjugate acid. Okay, moving on. This practice problem says write the formula for the conjugate acid for each of the following. Go ahead and pause the video and try to work this out on your own. Okay, let's go over this. So if we're trying to write the conjugate acid, then our conjugate acid is always paired with our base. And so each of these has to behave as a base. Bases gain H plus. And so let's add H plus to each of these and see what we get. So water behaving as a base would have to gain that H plus. And so we would have 3 hydrogens. And then we have to remember to add the charge as well. We go from being neutral to adding a +1. And so that gives us an overall +1 charge. So we have to remember to add charges too. All right, remember to add charges. Next up, we're going to have nitrogen with 4 hydrogens. Again, that's going to become overall +1 charge. That's our ammonium cation. And now for this one, it's going to have 1 hydrogen, 3 oxygen still, and then my charge is reduced to a -1 charge. And now for this one, I'm going to have 3 hydrogens and no charge. All right, here's a similar practice problem, but this one says write the formula for the conjugate base of each of the following. Go ahead and pause the video and try to work that out on your own. Okay, so we're supposed to be writing the conjugate base. The conjugate base is always paired with the acid. Acids lose H plus, and so we have to subtract H plus from each of these chemical formulas. And so if I subtract H plus, I have to go down to 1 hydrogen, and then my charge will become negative. Then I'm going to lose 1 hydrogen. That's not going to really want to behave as an acid, so you're never going to see this. It's just because that's ammonia. Ammonia acts as a base, so you'll never see this, but in theory, that's what it would be. We're just testing to see if you understand the concept. So I subtract H from this one, and there's no hydrogen to subtract, so like there is no H to remove. All right, now this one you'll go down to having 1 hydrogen, and then you'd have a 2- charge. And so the carbonate ion cannot behave as an acid because there is no hydrogen at all. All right, so here's another practice problem. In this practice problem, you have to write an equation with it reacting with water and acting as a monoprotic acid. So monoprotic means 1 proton acid. That's the literal translation of that. So we're talking about removal of 1 H+ ion. And then label the conjugate acid and base. Go ahead and pause the video and try to work it out on your own with each of these behaving as an acid. Okay, let's write these equations out. So for our first one, we have HBr reacting with water. And we're told that HBr has to behave as my acid, which means water has to behave as my base. We were told that in the problem. And so then bases accept H+. This one donates H+. So this one's going to give up its hydrogen to become Br-, and then water will accept that proton to become H3O+. Check to make sure that you're balanced. And so 1 bromine, 1 bromine, and then a total of 3 hydrogens and 1 oxygen. And so we're good. All right, for our next one, we were also told that this one has to behave as an acid and water has to behave as a base. We were told that in the problem. And so this one's going to give up its hydrogen. And so that's going to become SO4 2-, and then water will be gaining that proton to become H3O+. Good. All right. Next up, we'll quickly go over acid and base strength. So in an earlier chapter, we defined strong electrolyte and weak electrolyte. So strong versus weak is a term depending on how much it ionizes in solution. And so strong electrolytes completely ionize, whereas weak ions mostly do not ionize. Mostly don't ionize, but there is a small amount of ions. So we defined those strong and weak electrolyte terms earlier. And so anytime we see this word strong acid, we need to be thinking about how it completely ionizes in solution. And so HCl is a strong acid. That H+ is going to go onto a water molecule to become H3O+ and Cl-. And then in the solution, there are no HCl molecules. And so this is strong. A weak acid and a weak base, once you put this in, you will have some intact molecules and very few ions. Mostly neutral molecules. And so that means that this one is weak. So the list of strong acids and strong bases is much shorter than the list of weak acids and weak bases. And so if you see one of these acids, they are strong. These are listed on your green sheet. These are listed on your green sheet. And so these are the strong bases. These are the strong acids. I highly recommend you memorize the ones that are starred because those are going to come up again over and over again, especially when we're writing our net ionic and complete ionic equations. And so you have to make sure you recognize that these are the strong ones. Just right off the top of your head without even having to look it up. Here's a practice problem. Identify each of the following as a strong or weak acid or base. Remember, if it's not strong, it is weak. Pause the video and try to work this out on your own. Okay, let's go over this. HBr, that is on your list of strong acids, so it's a strong acid. NaOH is also on your list of strong bases, and so that's a strong base. This one is on your strong acid list. So OH minus is a clue for a base. H plus listed first in the chemical formula does mean acid. And so since this one's an acid, but it's not a strong acid, this one must be a weak acid. And this one is it is a base because of the OH minus, but it's not on the strong bases list. So this one is a weak base. So that concept of acid strength can be used to kind of relatively predict your molarities. So remember, if it's a strong acid, then it completely ionizes in solution, or a strong base completely ionizes in solution. If it's weak, then it's mostly not ionized. So figure out the molarities for each of these. If you ever see brackets around something, that means molarity. Okay, so this one is a strong base. KOH is a strong base. And so when this reacts in water, so KOH reacting in water would produce, or I'll write it all out so that you can see the reaction with water. I won't shortcut. So this is a base, which means water would have to act as an acid. And so the H from here will go over onto my OH. My K is just a spectator ion. And so I get my OH minus here will grab onto a proton from water to become water. And then water loses a proton to become OH minus. So that's a 1-to-1 ratio. And so since this is a strong base, my molarity of OH minus is a 1-to-1 ratio. You're supposed to write the minus sign on the inside of the bracket. So it's a 1-to-1 ratio. There. For this one, this is a weak base because it's an amine. So since this is a weak base, then our molarity of OH minus, we don't know exactly because we're not in Chem 1A and we're not going to calculate that. Our molarity will be much less than the original ion. And so that's much less than. And now for this last one, we have 2 OH minuses, so our strontium hydroxide reacting with water. That's a strong base. And then my ions are strontium, and then OH minus and water. And then to balance, I'm going to need 2 of those. So since this is a 1 to 2 ratio, I could write it out to show you. That's not what I meant to write. That's moles per liter. But I can cancel out just the mole numerator and end up with moles of OH minus. And then I will have, oh, I left out a 0. That'll be 0.050 molar OH minus. Okay, here's another practice problem for you. Go ahead and pause the video and work it out. This time we're concerned about the H3O plus concentration. Okay, let's go over this. So HCl reacting with water. We will have H3O plus ions, and we have Cl minus ions. That's a 1-to-1 ratio, and so we will have 1.5 molar H3O plus. 1-to-1 molar ratio. This is a strong acid. This is a weak acid. So since this is a weak acid, we won't work out the exact molarity of H3O plus. We just know that our molarity of H3O plus will be much less than 3.0. So my molarity of H3O plus will be much less than 3.0 molar. Generally speaking, the stronger the acid, the weaker the conjugate base, because the reaction's really being driven in one direction. And so since this is a strong acid, then Cl minus behaves as a weak base in the reverse reaction. So weak that it can't really even go backwards. But AHF is a weak acid. And so the F minus ion is a stronger conjugate base. It's still not a strong base, but is a stronger conjugate base than Cl minus.